Hey there. In this video, I want to walk through the correlation and linear regression PowerPoint for this week. Let me set up. Let me go forward. There we go. All right. Uh, in the last module, we talked about ways of describing data using measures of central tendency and variability. Now we're talking about ways to describe when we have bivariate data or two variables. How do uh, how do two variables do they trend in the same direction? So here's some examples of what we mean by like bivariate data. So like the heights of men and women, the age of married couples, years of education and salary. You can kind of think about how each one of these may trend together in some way. Uh, I think you may hear we're going to kind of our measure of the relationship between bivariate data is the Pearson's product moment correlation coefficient. You may also hear it called like a zero order correlation coefficient. And this, usually when we say the word correlation, they're probably referring to this measure, to Pearson's R. And this is a measure of the linear association between two variables. And typically these variables are measured on an interval ratio scale. This is our most common correlation coefficient, and you'll typically see it symbolized with the letter R. Here is the formula for calculating Pearson's R, both in like the raw score form and in the covariance form. You don't have to memorize it. We're going to let the computer calculate the correlation for us. But if you do want to know how it was calculated, you can see between the raw x and y values for each observation of that variable, or you calculate it from the covariance of the two variables. And the covariance here is really just another measure of the linear relationship between two variables. The only thing is it's scaled in the same metrics as x and y. So it's not bounded by like -1 and 1 like the correlation coefficient is. So it's usually not quite as useful, but it's more useful for making mathematical manipulations. Our next one. There we go. So let's talk about some properties of the correlation coefficient. Correlations all range between -1 and 1. The sign on there, whether it's positive or negative, indicates the direction of the relationship. The positive sign means they're both moving in the same direction. Just as x increases, y increases. Or as x decreases, y decreases. They're moving in the same direction. The negative sign indicates that the two variables are moving in opposite directions. So as x increases, y decreases, or as x decreases, y increases. They're moving in opposite directions. The number on it indicates the magnitude of the relationship. So the closer to 1 or -1, the stronger the relationship. The closer to 0, the weaker the relationship between the two variables are. So a correlation of 1 or -1 indicates a perfect linear relationship between the two variables, and a correlation of 0 indicates there's no relationship, or no linear relationship, rather. Uh, the larger the absolute value of R, the stronger the linear association. So in this example here, like a correlation of -0.8 would be a stronger association than a correlation of a +0.4. Remember, the sign just indicates the direction of the relationship, whether they're moving the same way or in opposite directions. But the number indicates how strong the relationship is. Also, correlations are unaffected by linear transformation, so we could multiply or add a constant to all of the values of x or y, and the correlations would stay, the correlation coefficient would stay the same. So it's unaffected. We'd say it's unaffected by linear transformations. We typically graph bivariate data using a scatter plot. So we would have uh, a plot with little dots for where the value of their value of x and y is, and it comes together. Uh, we usually graph on the y-axis, the vertical axis here. Is the response of the dependent variable, and on a horizontal axis is usually where we put our independent variable. Scatter plots give you a nice visual of the relationship between X and Y. You'll be able to tell whether it is a linear or maybe a non-linear trend. And it's a good way to spot outliers too. Is there a value out here that's not following along with the trend? And if you'd like some more information about scatter plots, you can click on this link here. It'll pull up this website, and you can read a little bit more about scatter plots there as well. Let's take a look. So let's take a look at this scatter plot. So here we have wife's age and husband's age. So here's what a couple things we can tell from this graph. Uh, it, it looks like there's a nice linear relationship, right? That as husband's age increases, wife's age also tends to increase. You can kind of see that coming along here. This would be an indication of, what kind of relationship do you notice here? Should be an indication of what this would be a positive relationship, right? Because as we increase in husband's age, we increase in wife's age. And the little dots here are just formed by, this husband here is around 50, and the wife here, come across here, is about 42, 43, something like that. Uh, that's how you graph each one. What do we notice at this kind of relationship? Here we have agreeableness and problem behaviors. So it looks like as agreeableness tends to increase on the scale, problem behaviors tends to decrease. So that'd be an example of a negative relationship there. What about here? This one looks more like kind of a random scatter, right? It doesn't seem we're not really noticing any kind of trend one way or another. So this would probably indicate that there's no relationship. So the correlation here would probably be really close to zero with these data. What about here? What kind of relationship do you notice? This seems more like a nonlinear relationship, right? Where we have a nice like curvature to the graph here. If we see some pattern like this where we have a curve to the graph like that. When we're trying to force a linear line to it, Pearson's law will underestimate the relationship for a non-linear trend. So we'd want to use a different kind of correlation to look at that relationship. Oh, there we go. Oh, how do I erase that? Give me 1 second. There we go. Uh, these are some fun links you can check out. It'll give you some scatter plots and you can guess what the correlation might be. So you'll pop up like this and you can kind of play here. Like this one looks like, you know, as X increases, Y starts to decrease. So it's probably a negative correlation. Uh, the tighter the dots are together, it's going to indicate a stronger relationship. So I'm going to probably say like a negative zero point 0.7 here. This one looks more positive. Uh, so I'm going to probably say that's our positive 0.73. This one's positive and they're all pretty tight with one another. So that's probably the 0.98. And this one's negative. They're a little bit tighter than this one. So that's why I'm going to say the negative 0.86. And then we got to write. So you can play around with that. The other plot has the same thing. There's a nine, kind of guess the correlation. One thing to note, correlation does not imply causation just because the two variables are related to each other doesn't necessarily mean that X is causing Y. We'll talk in the research design chapter more about how to establish those causal relationships. There's also something called like a spurious correlation. This is what happens when a relationship is wrongly inferred between variables because we haven't considered a third variable. And sometimes correlations can be due. Sometimes the relationship between two variables is spurious because there's some other variable there. A classic example you always will hear is like ice cream sales and crime rates are positively correlated. That as ice cream sales increases, crime rates tend to increase. But they're really probably both caused by a third variable that we're not measuring, which is temperature. Ice cream sales tend to increase when the weather increases, and crime rates tend to increase when the weather increases. So both of them tend to be a little bit higher in the summer months. So that's an example of what might be a spurious association. So sometimes when you see a correlation between two variables, you might want to ask yourself, is this a true relationship or is it caused by something else? That's why we have this, make this statement that correlation does not imply causation because we want to rule out these other factors before we make that assessment. Here are just some factors that affect the magnitude, so the size, that number, and the correlation coefficient. Remember that Pearson's R is an index of the linear association between two variables. Uh, so if Pearson's R is applied to variables that are not linear related, it'll tend to underestimate the relationship between the two variables. When groups become less homogeneous, they're less variable, the correlation coefficient tends to decrease as well. And then outliers tend to have uh, uh, a strong effect on the correlation coefficient. Here's an example of the outlier. We can see that we have the scatter plot, the correlation when the outlier is included in the calculation of the correlation. The outlier kind of pulls that trend line towards it, which kind of then attenuates the correlation coefficient. And when we take out the outlier, you can see the strength of the relationship uh, increases. Okay, here's a good question. Let's say that grades are correlated with IQ in an honors math class and also in like a regular math class. Which do you think would have the correlation would be higher? The answer is the regular math class because of our second point here. When the groups become more similar to each other, it kind of attenuates the correlation coefficient. So the correlation between grades and IQ is likely to be higher in the regular math class where there's more variability. because students in the honor class should be more similar to each other. They should all tend to have relatively high IQs and relatively high grades, so they're going to be less variable. Here's an example I made of this to kind of demonstrate. Here is some folks. I just made up a scatter plot here. The honors class here, they all have really extremely high IQs actually. 150 to 200 here in that range. Uh, but they all have really high IQs and they all have really high grades, right? So the correlation here is a little bit weaker than in the regular math class where it's more variable. You have some people with lower IQ, some students with higher IQ, some people with lower grades, some folks with higher grades. So that's kind of an illustration of how the correlation can be attenuated when the groups are more homogeneous. Here are just some kind of rules of thumb for interpreting the correlation coefficient. I got these from Henkel's stats book. You can see the citation here. I would take these kind of with a grain of salt. I mean, you really need to know the literature in your area to know like how strong the correlation might be. What are others finding in that kind of relationship in that area? But generally, this is what we think about when we talk about like it's a correlation. Like, a correlation less than, zero point 0.3 is probably a pretty weak correlation. Uh, some requirements for using Pearson's R correlation. The sample is randomly selected from the population. The traits are being measured are approximately normally distributed. The measurement level is at least interval. Uh, and the variability for X and Y are similar. Also, the other big thing is that we're examining like the linear relationship as well here too. We can also use R. We can interpret R in terms of variance explained. We can square the correlation coefficient, and then R squared equals the proportion of variance in Y that can be associated with X. You can think of it more as like of an effect size, like how much variance in Y is explained by our knowledge of X. In the regression literature, we'll call this like the coefficient of determination. And this is again a variance explained effect size. So you see the R squared is 0.32, which is saying, so we're saying that 32% of the variance in Y is associated or can be explained by Y's association with X. All right, so you can run through some of these practice exercises as well too. The answers are in the notes section of the PowerPoint. So I encourage you to go through them, try them out, and check out the answers in there. So we'll go through one of them here. So for a certain class, the relationship between the amount of time spent studying and test grades earned was examined. It was determined that the amount of time they studied increased, so did their grades. Is this a positive or negative association? Since as time increased, grades also increased, that'd be a positive correlation. What do you think the second one would be? The relationship between the amount of time spent studying and the amount of time socializing per week was examined. It was determined the more time students spent studying, the fewer hours they spent socializing. Is that a positive or negative association? You can also go through these true or false questions. The answers again are in the notes section as well. Um, So the correlation between height and weight is one. That's probably false. It's definitely a positive relationship. As height increases, weight tends to increase. There's probably not a perfect one-to-one relationship. Uh, it's possible for variables to have a correlation of zero but still have a strong association? This is kind of a tricky question. The answer is actually true. And this is a great example of that. Remember that R examines Pearson's R looks at the linear association between two variables. These variables, look, this is more of like a quadratic relationship. We're increasing up into a point and then we start decreasing again. The linear association is probably pretty flat over the whole trend, but there's definitely a strong relationship here. We're just not able to pick it up with this correlation coefficient. Uh, okay, two variables with a correlation of 0.3 have a stronger linear association than two variables with a correlation of 0.7. That would be false, right? Remember, the positive and negative just tells us about the direction, the magnitude, how strong the relationship is. We just look at the absolute value of the number. After polling a certain group of people, researchers found a zero point 0.5 correlation between the number of car accidents per year and the driver's age. This means older people tend to get in more accidents. Uh, so it's a positive correlation, right? So it's saying that as age increases, the number of accidents also tends to increase. So accidents tend to increase with driver's age. It's not necessarily saying that that's a causal relationship, but there's some type of relationship between those two. Uh, to examine bivariate data graphically, the best choice is two side-by-side histograms. No, right? It's our scatter plots that we talked about before. And a correlation of 1.2 is a stronger relationship than a correlation of zero point 0.2. This one's kind of a tricky question too. There's no such thing as a correlation of 1.2. Remember, the correlations range between -1 and 1. There's a handout on Canvas that talks about some other correlation coefficients, so I'd encourage you to read that. We're mainly focusing on Pearson's R here, but there are many different other kinds of correlation coefficients that you can check out. Like if we're looking at a correlation between like a nominal variable and an interval ratio variable, we can use like a point biserial correlation. If we're looking at the correlation between two ordinal variables, we could use like Spearman's rho correlation. We can also use Spearman's rho to look at a correlation between two interval ratio variables. It's really more examining more of like a monotonic relationship. So something that would kind of like gradually increases, but not necessarily in like a linear fashion. So be sure to check out the document on Canvas. There's a lot more detail about some of these other correlation coefficients. Let's talk a little bit about linear regression. Bivariate linear regression attempts to model the relationship between two variables by fitting a straight line to the observed data. So you can think of our scatter plot. We're trying to fit like a straight line to it. You can think of that line as like the measure of central tendency for our two variables. Like what one line would best represent the relationship between these two variables. And that's what linear regression tries to get at. In this class, we're going to discuss like what's called ordinary least squares regression or OLS regression. You'll go into regression a lot more in Stat 2. So this is just a very brief introduction into simple linear regression where you have one dependent variable and one independent variable. We just have bivariate data. In Stat 2, we're going to extend that to include multiple independent variables to examine how, like, the linear combination of these independent variables, the impact it has on the dependent variable. But right now, we're just looking at the simple linear regression. It's just a bivariate relationship. So you can really think about it as uh, that kind of measure of central tendency for those two variables, what line best fits those two, the relationship, best explains the relationship between those two variables. There's really two main uses of regression analysis. One is for like prediction purposes, and one is for explanation. So, say we want to try to predict end of course GPA, we might use some things like high school GPA, SAT scores, motivation. The goal really in like using regression for prediction purposes is to find the most parsimonious equation with the fewest errors, just to make the best prediction model. They use various types of regression models all the time, to make like predictions online, like you're shopping online and it keeps like recommending you, you might want to like this type of tennis shoe or something. So it's trying to take your old search history and what you're currently looking at and build a model to predict what you might be interested in. That's all based on a type of regression model. In academia, we kind of mainly use regression for more explanation type purposes. We want to examine, what factors influence or what factors are related to some phenomenon. And so we'd use it for more predictive purposes. The equation for linear regression is, you probably remember this from like fifth grade math, y equals bx plus a, or maybe y equals mx plus b, uh, where the linear relationship between x and y can just be expressed by some constant value plus some change value, some slope. Uh, and you might remember this is like the kind of rise over run coefficient. So y here is our predicted score, so it's our outcome, our dependent variable. B here is the slope of the line. That's the rise over run, right? How far we go over and up. What's kind of that angle of the line, the slope of the line. Here, that's what the B represents. And the A here is a constant or the y-intercept. It just says, where does that line cross the y-axis? It just kind of anchors the line at where it crosses the y-axis. You're not going to have to, you won't have to uh, compute the regression line yourself. I'll show you how you can get it out of SPSS. Uh, but if you're just interested in how the equation is, how you would calculate the terms, you can see that the slope coefficient is related to the correlation times the standard deviation of x and y. And the constant is equal to the mean value of y minus the slope of the line times the mean value of the x score. So this is how it's computed in simple linear regression. We have more than one independent variable. We got to use some matrix algebra to do it, but in the simple case, these simple formulas work. Again, you're not going to have to do this by hand. I'll show you how to get it out of the computer in another video. So let's look at our example here. We're going to use regression for prediction purposes here. So we have a local tennis club, charges a fee of $5 per hour, person annual membership fee of $25. With this information, what's the total cost of playing tennis? Well, we can represent the total cost of playing tennis with a linear regression equation that describes the relationship between the total cost and the number of hours we played. Right, so so the total cost y here is equal to, it'd be 5 times the number of hours we played plus the membership fee is our constant, right? You have to pay that every time. So what's the cost if we spent 100 hours playing tennis? It'd be $525. The slope or the B coefficient here is just defined as the amount of change in y that corresponds to a 1 unit change in x. It's that rise over run. That gives you the horizontal, that horizontal distance. Uh, so if the B coefficient is zero point 0.3, it's saying that uh, a 1 unit change in X corresponds to a zero point 0.3 unit change in Y. So it gives you the amount of change in Y that corresponds to a 1 unit change in X. So if we were to change X, if we were to increase X by 1 unit, what would we expect Y to increase or decrease by? So if it's negative, it's saying that Y is decreasing. And that's the regression constant. Or sorry, the regression coefficient. The regression constant is the y-intercept, right? It's when x is 0, what is the value of y? So it kind of anchors it. Where does it cross the y-axis? That's where x is 0. So when x is 0, what's the value of y? That's the regression constant there. So in our tennis example, like if we played 0 hours of tennis, we would still just pay $25, right? That's when our x value is 0, what's the minimal cost here? So that's how you can think it still represents the same thing. And then our b coefficient here, 5, our slope, it's, for every 1 unit increase in x, y increases by 5 units, right? For every hour that we played, our total cost increased by $5. So you see, it's still interpreted the same way. That for every 1 unit increase in X, Y increases by B units, whatever that is. So let's go through this example. In a study of the relationship between education and income, a researcher finds that people with only grade school education have an income of $12,000 a year, and each year of education adds an additional $5,000 to a person's income. This would yield the following prediction equation. Y would equal 5,000 times X plus 12,000, where annual income depends on the years of education. So what's the predicted income for someone with 16 years of education? We could just plug 16 in right here, and we would get their estimated. So using this prediction equation, we would estimate that their annual income would be around $92,000. Here's a graphical picture of how the regression line is drawn through a pattern of points. So we have a scatter plot. Here is our y-intercept, right where it crosses the y-axis. You can see it's the distance between the x-axis, the distance from the 0 point of the x-axis up to where it crosses here. And you can see the slope of the line is the rise over run here. That gives us our slope effect. So the regression line kind of identifies the center, or again, we talked about like the central tendency. It's kind of a measure of central tendency between the two variables. It identifies the relationship. The line kind of gives us like a simplified description of the relationship between X and Y. So the regression line is determined by this method of least squares. If it's aligned in such a way that the sum of the squared distances from each data point to the line is minimized, uh, and then we get a good picture here. So we try to fit a line to where the vertical distance between each data point in the line is minimized. We minimize the squared distance between each data point in the line. Same thing here when you had a bunch of points here. The ordinary least squares gives you the line of best fit that minimizes the sum of the squared distances between each point in the line. There'll be no other line that would have a smaller uh, sum of squared differences between each point in the line. That's what it identifies here. We're trying to identify a line that describes the trend in the data, such as a change of X would reflect an average, some type of average change in Y. And that's the OLS method sort of minimizes that sum of the squared distance between each point and the line. This distance here that's being minimized is what we call our errors of prediction, right? The error is the distance between each point and the line. So you can see the green dot here, this one right here. Uh, its value is 1.3. Uh, its predicted value here, and it's pretty close to like zero point 0.2. Uh, So the error in prediction is around like negative zero point 0.7. So it's negative zero point 0.7 units away from the line. Uh, so we're trying to minimize these errors. Again, same kind of caveat that we had in correlation is regression X and Y does not imply that a change in X causes the change in Y. When we go to our research design chapter, again, we'll talk a little bit more about kind of establishing that causal relationship and what conditions that we need that must be met in order to do that. Uh, some assumptions with simple linear regression here. Our outcome variable, we want it to be continuous. We want it to be measured on the interval ratio scale. If we have a nominal variable, this isn't the right regression analysis for it. There are other regression analyses that are more appropriate for variables that are not measured on the interval ratio scale. But the one we're talking about, our outcome is measured on the interval ratio scale. Since this is simple linear regression, our x variable our x variable can really be measured on any type of scale, but most likely it's going to be on the interval ratio scale too for what we're doing. But it could be a nominal or categorical variable as well. And we'll talk about doing those in stat too, if you take it. And again, this procedure examines the linear relationship between the independent and dependent variables. So looking at the linear relationship between X and Y. And that's all I have for this module. Uh, if you have any questions, please don't hesitate to reach out to me. I'm here to help. And thank you. Bye.